Now, the first thing I want to do is to go back, I suppose, really, and explain something in a little bit more detail. It's not going to take a long time, actually, but and the reason I'm doing this is because it will probably be useful to some of you for the assignment. Not at the early stages of the assignment, but possibly at the latter stages of the assignment. So that's why I'm doing it. I'm covering it. And what I'm going back to is this very, at this stage now, you would consider it a simple little stack. So my stack consists of my movies table. I've got, okay, some seeding going on here. We're not really interested in that. Here I've got a lambda, and this lambda reads from the table, and it reads individual items from the table. And okay, I'm generating a URL for that lambda here. That's okay. And this is the line I want to focus in on. And we know that the effect of the line that I've highlighted there is to allow or to give the lambda function the privilege to access the table. Or more technically, the effect of the line that I've highlighted is to add an IAM policy to the role, to the IAM role that is attached to the lambda, where the policy grants it the privilege to read from the table. And so I can actually find, using the console, the effect of the line that I've highlighted there. And I know I've done this before with you, but so if I go into the Lambda service, so I've already deployed this stack now a few moments ago. And the function is this one. By the way, the other function is the other lambda is a lambda that's actually created by my seeding custom resource, but that's not really relevant today anyway. Okay, so if I go into this lambda function, and if we look at the permissions associated with the lambda, and we know where we find those is if we go into the configuration tab, and then we have the permissions selected on the left here. And here's the role, the IAM role, the identity and access management role that was created by the CDK stack via CloudFormation for me. I did say that each lambda gets its own role. That's just a convention and good practice. So if I select this role to see what kind of permissions does this role have. So this brings me over into the IAM console. And if I poke around here, I can see that there are two policies attached to the role. The first one is the standard Lambda policy, and that policy essentially allows the Lambda to write to CloudWatch logs. This policy here, though, the second one, is the one that's linked to the line of code that I highlighted there in the stack. And so if I click on this policy to see the detail of it, it's an IAM policy, which again, admittedly, those of you that are not doing the CloudStream, may need to just go back and quickly review what you covered in IAM. Those that are doing the CloudStream are probably dealing with these on a daily basis. And so when I look at this policy here, we can see, it's all related to DynamoDB and the various actions that are allowed are specified here. So it's service : action. And all of the actions are related to reading actions. You know, there's the query, the scan, the get item in particular. That's actually the one that's being used by my Lambda. It doesn't actually use the other ones, as it turns out. And I can prove that to you in a moment. So that single line of code generated this policy for me. The policy was attached to the role, and the role was attached to my Lambda, and voila, my Lambda is able to read from the database. But supposing I didn't have this nice convenient method available to me. So if I disable that, clearly I'm going to get an access error. How can what I'm trying to get to here is, how can I actually generate an IAM policy and attach it to the role of the Lambda? How can I do that programmatically within my CDK code? Because there will be occasions when you want to use, or when a person wants to access a service from within a Lambda, and there isn't these kind of nice, convenient methods available to you to grant the Lambda the privileges that it needs to access the particular service. Sometimes you actually have to write the IAM policy yourself and attach it to the role of the Lambda. So programmatically, how do we do that? And how you do it is what I've actually brought in here. So if I uncomment that, so the way you go about it is you refer to your Lambda function. There is an add to role policy, which you can, which is kind of generic really, and the name tells you what the purpose of the method is. It's you want to add a policy to the role of the Lambda. And the arguments that this method takes is it expects to receive a policy statement instance, and that's what we're doing here. We're creating a policy statement instance, which is contained within the IAM package, which I've imported at the top. And so we'd have to look at the constructor for this guy. But what the constructor expects is an object that's structured like this. And the parts of the object, are very similar to, this actual document here, this JSON document. It's not it's a close enough copy. I'd say you can almost copy most of it, actually, as it turns out, but some of it you can leave out and accept the default values. And so my policy looks like it's allowing certain actions, and I'll come back to the resource in a second, but the actions part is expected to be set to an array. And this array is an exact copy of this array here. That's what I did. I just took an exact copy of it and pasted it into my code. And also the policy, sorry now for flicking back and forth, but the policy also refers to a resource. Now you could be lazy and just say the resource is just set it to the asterisk character, which means any resource, and that's actually okay in some cases. We can be specific here though, because the resource is actually referring to, this is the ARN, the Amazon resource number for my DynamoDB database. And I can actually get at that within my CDK code, which is what I'm doing here, right? If you refer to your table and there's a property on this movie table object called table ARN. So that evaluates to the full Amazon resource name for the particular resource. But if I didn't know how to do that, then and that's a string. But if I didn't know how to do that, then what you can do is just go asterisk, and that'll. Sorry, that's not an asterisk. My asterisk character. That would be okay as well in some cases. You don't have to be specific about the resource. It's obviously slightly better if you are, then you're following that principle of only allowing the privileges that the Lambda actually needs. So that's my resource. They're my actions, and I'm allowing these actions. So now I'm putting forward the idea that if I actually get rid of this statement and leave this code in instead, it's going to be the same net effect. And so let's prove that. If I redeploy, and what I'm actually going to do as well is, if we looked at the Lambda just very briefly, I mean, we've seen it before, but the only interaction that my Lambda does with the table is it does a, where is it? One movie by ID. Let's see. Oh yeah, it does the well, in terms of the client and the document client, it does a get command action. That get command is when that is compiled right down, and there's a request across the network from your Lambda service to the DynamoDB service. That get command equates to, from the DynamoDB services perspective, it equates to this action here, get item. So in fact, the action that I've highlighted there is the only one that Lambda needs. But just for now anyway, what we'll do is we'll take away, let's say, these two actions. Why not? Okay, we'll just take away those two. So whereas when this statement was active, the policy that was attached to the role included the query and scan. Now I'm actually removing the query and scan actions. So when I eventually deploy this and I look at the policy, it should no longer have the query and scan. So that's proving to me that, this code here is actually doing what I expected it to do. So let's deploy anyway. Or redeploy. The other thing, actually, as a by the way, it's not linked to what I'm covering here now at all, is I'm kind of jumping around the place now, but the seeding code here, right? Just remember that the seeding code only runs when you deploy your application for the first time. So let's supposing I deploy this for the first time, the seeding will work. If I make a change to the seeding and then do a redeploy, you will not see those changes impacting at all on the database, because the seeding code only runs when you deploy for the first time. So if you do have to make changes to your seeding, having deployed the application already, then simply what you have to do is you have to destroy the application and deploy again. And that deploy then is effectively a first deploy of your new application, if you like. So that's kind of caught me out initially. I was making changes to my seeding, but I couldn't see the changes. I was adding more records to the table, I think. But when I was redeploying for the third or fourth time, it wasn't actually following through, and that's the reason why. Okay, back to what we're really interested in for now anyway, is this stuff here. So let's do a redeploy. And because I've changed some part of my application's IAM policies, it's always going to ask me, are you sure you want to do this? That question doesn't come up if you're not changing any IAM issues. So we let it work away there in the background. And if I go back here, and I'm just going to close off this because it's going to create a new, it probably creates a new role now actually, and a new policy for that role. So that won't work. And I'll go back to my Lambda. Close off that as well. Okay, so it has deployed at this stage. And if I do the same thing now, I go into my Lambda function. I'll just do a manual refresh here. And into the permissions and the role. There are still two policies, and this is the policy that is now being generated by my my specific IAM code, if you like. And you can see now, if you look at all the actions here, the scan and the query are gone now. So that's proving to me that, okay, it is taking my policy now as opposed to the policy that was generated by the grant read write access method from earlier on. And does it still work for me? I guess it does. Let's see. I tested it earlier, so this is the actual URL of the Lambda, and I'm adding on my query string on towards the end. So if I do a manual refresh, it should still work. And it looks like it does. And the last thing I'll do is, because I know exactly what my Lambda function does, I can deduce that it doesn't really need all of these. I mean, they're only all read actions anyway, so they're safe, but I can actually pare down my policy just to get item. And then I'll save that and redeploy again. Close off these because they're now out of date. While we're waiting, the other comment I would make in relation to the assignment is, I suppose it goes without saying in a way, but sometimes the obvious things need to be mentioned. You know, you obviously have to think about your table structure and your primary key and getting that right. I mean, statement of the obvious, I suppose, but there's a reason I'm saying it to you, I guess. So do, and obviously, you know, if things aren't working and you might think it's because the table primary key is incorrect or whatever, or some part of your table definition is incorrect, then, you know, you have to obviously tear down the entire application, do a CDK destroy and CDK deploy after you've made whatever relevant changes. Okay, so it's deployed. And again, let's look at it from the console's point of view. So we're back at the Lambda level. I'll just do a manual refresh. My role. Into the policy. Okay, and now the only action is get item. And hopefully it still works. So if I do a manual refresh. Yeah, it looks like it's still working. If I change the movie, just in case it's caching, which it isn't, but I think the other movie I had was 4, 5, 6, 7, I hope. Yeah, it's picking that up as well. Is it 4, 5, 6, 7? Oh yeah, there it is. There's the movie ID 4, 5, 6, 7. So yeah, it's still working. Okay. The overarching point I'm trying to get at is, or trying to make, and I'll repeat again, is if you have, well, in our case, it's going to be a Lambda, but it doesn't have to be. If you've got a Lambda that wants to use a service, but that service, you know, isn't as, in terms of its CDK support, maybe it's not as rich as DynamoDB, then you may have to generate an IAM policy and attach it to the Lambda's role. You may have to do that manually, so to speak, as in you may have to code it like this yourself, rather than having the convenience of a simple method that does it for you. Okay, I'll pause for a second just in case there are any questions. No? Okay. So back to the main topic of today. So if I go into the slides, I want to walk my way through this set of slides here. This stuff now is going to be, I would describe it as theoretical, but it's important that you have an understanding of the points that are being made by the slides, really, that you've got a kind of high level understanding of how we architect, in particular, server-side applications and how the architecture of those applications have evolved over time. So we are looking at a bit of the history of it as well, but it's always important to have an understanding of the history of how we finish up to at where we are right now. But there's no code here, it's just all talk, if you can bear with it. So application architecture is the title. Now we know when we look at the world today, the business world today, I suppose if I put it that way, then, you know, all businesses use software as a central part of any type of transactions that business carries out with other businesses. So software is really central or core to any type of business today. That wasn't always the case. And in the first bullet point here, I'm referring to the title of an article in a journal back in 2011, where the person was essentially kind of stating, stroke predicting, that really software is going to be central, or it's eating the world, as in it's becoming central to how all businesses operate. And that was often reflected in the boards of businesses, in that one of the board members' title would be the Chief Technical Officer, or CTO. And that reflected the importance of software to any type of business organization. And we know that's the case today, but back in 2011, it was less so, and certainly prior to that, even less so again. The second bullet point is saying, and it's an expression or a view that we hear a lot if we listen to any kind of business news on the radio or TV, and it's this idea that businesses need to be innovative and they need to be agile. They need to be able to react quickly to changes in their environment and in their customers' needs and demands and all this kind of stuff. So this idea of businesses having to be agile and adaptable to their changing environment, because it can be a volatile and uncertain environment, and it's certainly complex. And so if we take that point and we take the point that software is central to any organization's operations, then that must mean that we as developers of software, we need to be able to develop software in a rapid, frequent, and reliable way. Okay, we need to be able to turn around new features for our business customers rapidly. We can't say we can give you that feature in 6 months' time or a year's time. The turnaround of features needs to be frequent, and obviously it needs to be reliable. Now, so that's where we come in, really. How do we as software developers achieve that aim or that objective? And I'm saying down the bottom part of the slide that when we try to measure these characteristics of rapid, frequent, reliable software development, then you could say that there's two parts to it. There's and these are terms that we sometimes use in software development, the velocity at which we create software, where one way of measuring velocity, I'm saying, is lead time. If you think about the time gap between when you make a commit to a Git repository or GitHub repository, the time between that happening and the changes that you've made actually being reflected in the deployed software. Now, whether that be the deployed software that's running on some sort of staging server that's just available to the software development team, or whether it's available, it's the deployed software that's being used in production. They're two very different things. But let's say it's just the staging deployment. By staging, I mean it's essentially a carbon copy, or as close as possible to a copy of the production deployment environment. But by staging, we mean it's just available to the software development team and maybe to the customer for review, but certainly not to the end users. And, we can see, even when we're using the CDK tool, for example, that is almost within seconds, really. Now, obviously, we're not doing any quality control steps between deployment and exercising our application. There should really be some sort of automated testing run between the time the software is deployed to the staging environment. There should be some automated testing carried out straight away to make sure that the software is reliable. We haven't looked at automated testing, nor will we, but it's also a big part of the whole software development lifecycle. But we are down to the kind of minutes kind of measure. or should be. Certainly that wasn't the case if you go back maybe 10 years. The frequency of deployment is another way of measuring velocity. And the way things work today, you know, if you've got a team working on a software project, then and each member of that team is tasked with developing some feature or fixing some bug or doing some bit of refactoring on a piece of code, then you know, with the availability of the tools that we have, like source control and the various other automation tools, testing automation tools, and deployment automation tool, which is essentially kind of what the CDK is, then, you know, the time gap between having completed some piece of code change and seeing it being exercised within the context of the overall application deployed to an environment that is as close as possible to the production environment, that's kind of measured in almost in terms of minutes as well today. So that's obviously supports this whole velocity, and the kind of tools that we have available today supports our rapid, frequent, reliable objective at the top. Reliability, well, certainly the tools facilitate the rapid, frequent objectives. I'm being more specific about reliability here. And I'm saying reliability, one way of measuring that might be how quickly do we, as a software organization, how quickly do we fix problems that arise once we have deployed our software and maybe ran some automated tests on it. The automated tests throw up some sort of errors. How quickly can we turn around resolving those errors and redeploy a more reliable piece of software? Mean time to recovery, I guess. Sorry, change failure rate. Well, okay, change failure rate is saying how frequently, when we do carry out deploys, each individual team member does a deployment, how many of those deployments are actually faulty. And now that can be a reflection not so much on any automation that's going on there, but it can be a reflection on other quality assurance practices that a software house may practice. You know, what typically happens is an individual team member commits to, let's say, a branch on their GitHub repo. The commit is then reviewed by let's say the team manager or the project leader. And if the team manager or project leader is happy with the commit that has been made to the branch, then that branch is merged into the master branch of the GitHub repo. And it's only then when the merge happens into the master branch of the GitHub repo that the deployment to your staging environment actually happens. Now, there are issues that you haven't looked at all in any of your modules, to my knowledge anyway, but let's just move on anyway. The point being made here, though, is that successful applications, I'm saying, are ones that live for a long time. Now, what's a long time? I guess maybe 10, 15 years would be a good payback for any piece of software that an organization might buy from a software house. So the longer a software application is still considered successful by its customer, that's obviously the better from the software house's point of view. So, but the problem is, in that intervening period, there are obviously technology changes happening. And it would be nice if we could avail of the technology changes that are happening and somehow modernize our long-living applications, let them benefit from these technology changes. Is that possible at all? That would be, so we kind of have the best of both worlds. We've got software that the customer is happy with, but it's running on legacy technology. Can we somehow upgrade the technology stack, but still reuse the existing or a lot of the existing software? That's what I mean by modernization. Now, in the picture, then at the bottom, what we're saying is that there are really three parts to any software house's operations that will guarantee all of the objectives that we're talking about here. This reliability, frequency, what was the other one? Reliability, frequency, rapidity, and also the ability to modernize a long-living application. There are three things that a software house needs to have. It needs to have a good software development process, which we're not going to talk about. Okay, that would be a different module. Don't know if you've studied processes or life cycles anywhere. It also is determined by how the software organization is structured. And the third characteristic is the architecture of the application. Now, that's obviously is where we come in. But the other two pillars are equally important. And we'll see kind of later on that if we choose the kind of more modern architectures for our software applications, then they almost reinforce good processes and good organization as well. I'm being a bit more specific here. If we start at the top, which is the part that we're not really looking at in this module, but any software house today, really, in terms of the software process or lifecycle that they use, they should be following a DevOps approach, which you're kind of familiar with from last year, a little bit anyway. Maybe didn't go into the DevOps process in any detail, but you have a general sense of it. Another term that we use in relation to software process is CI/CD, continuous integration, continuous delivery. That kind of overlaps with DevOps a little bit. And it's kind of all about automating as much of the software development lifecycle as possible, automating the control of the changes made to the software, i.e. use something like Git and GitHub. It also refers to the testing aspect of the software development process. We try and maximize the amount of automated testing that is done within a software project. I suspect that's a topic you've not looked at, but I do cover it with other students on a different module. And thirdly, the automation of the deployment of your software to infrastructure. And we certainly know a lot about that from this module. But the process encompasses all of those aspects of software development: source control, automated testing, automated deployment, and some kind of manual aspects to it as well, like technical review of changes made to software, or what are referred to in GitHub as pull requests. In terms of organization, the thinking today anyway is that if you've got a group of people that are involved in developing and maintaining a particular software application, then you should try and break that group up into small autonomous teams. Now, when I say a group of people, let's say we're talking about in the 20 plus or even higher than that. So it's quite a large group of people that are responsible for developing, maintaining, and evolving a software application. The way you should structure that group of people is to try and break it up into small autonomous teams. And we'll come back to how that might be possible when we look at architecture and the modern approach towards architecture. So Let's talk about architecture. Generically, there are some what I call quality attributes that you can use to measure whether an architecture is a good architecture or not. These are often referred to as the ilities because they all end in ility in some form or another. And so going down to them, number one is the testability of your of the software that you're developing. And by testability, what we're saying is it amenable to automating the testing of the application? Now, we do testing in this module using Postman, and we do it's a very manual approach to it. It would be much better if we could automate the testing of our REST APIs. They happen to be REST APIs in our case. And there are lots of really good tools out there which allow you to automate the testing. Essentially, what you're doing is you're writing testing code, which is not an insignificant task. But once you've written your automated testing code, you can reuse it over and over again. But anyway, from a quality point of view, in terms of assessing the quality of the architecture of an application, it has to be an architecture that is amenable to automated testing. Number two, deployability. We know a lot about that. Is the application's architecture, again, is it amenable to automation of the deployment of the application? And as I said, we know a lot about that. So certainly if it's something that you're deploying to the AWS platform, then, and you're using something like CDK or indeed other comparable tools, then deployability is high, let's say. Number three, maintainability. And maintainability is simply measured in terms of how easy is it to understand and make changes to the actual software. And that's really somewhat comes down to how well your software engineers individually structure their code and use good naming conventions for classes and variables, etc., etc., and also follow good design patterns in terms of how they structure the actual code within a class and even the various classes that make up the application's architecture. Modularity. We know we have a general sense of what modularity means. The software is broken up into modules, but a module here kind of is bigger than a class, really. A module kind of refers to, let's say, a collection of classes, and that collection of classes implements some particular feature within the overall application. And that collection of classes, which we'll call a module, it has an interface that allows other modules to use it. Yeah. Like you've done Java programming somewhere along the line. You know that when you create a Java class, you put that class into a package. Then coming up with good package structure for an application would aid good modularity. But there's also this issue of the module's interface to the rest of the application. And I'm saying over here that the interface has to be impermeable, in the sense that if other modules want to use a module, all the other modules need to know about is the interface to the module. It doesn't need to know the internals of it, nor should it. And also the interface is clear and small. Okay, no more than that I'm going to say, but it is obviously modularity is a really important characteristic of the quality of an overall application's architecture. I'm being a bit woolly about it now because, you see, it depends on what languages you come from. I guess if you just think of maybe in terms of TypeScript, okay, we have classes and we can declare methods of classes as being public, private, or protected Now, the public methods of classes are obviously ones that can be accessed by other modules. And so packaging all of the classes that make up a particular module in a sensible way, making only certain parts of it publicly accessible, that will refer to the interface, the API of the module. Designing all of that well is obviously important. No more than that I need to say, and we're not going to get into it, but there are good texts on modularizing code. Evolvability in this context, evolvability refers to the kind of underlying dependencies that the software has. If we're talking about a Node or a TypeScript/JavaScript package, we're talking about the third-party libraries that it uses and the ability to evolve the packages on to more recent versions. How easy is it to achieve that? No, that's not too tricky in the case of TypeScript anyway. But of course, there can be problems when you start changing versions of a third-party package, and it conflicts with some other third-party package that you're using, which cannot work with the newer version of the one that you're trying to upgrade. So there are kind of headaches associated with evolvability of third-party software that you might be using. But again, as we said at the outset, technology moves on, and certainly third-party packages, they're always being upgraded, and you'd like to keep up to date with the most recent versions of them. But it may not be a straightforward thing. It's just simply going into your package.json and just changing them. So they're all qualities, I'm saying, of a good architecture. And the other ones I mentioned down here are equally important. The scalability of your application, that's key as well, to certainly if your application is deployed to the web, it needs to be scalable. And does the architecture actually facilitate that? And the last one is fault tolerance. If your application is deployed to the web, servers can go down, and how well does your software react when certain parts of your network is inaccessible? You may actually have to build that into the functionality of your application somehow. It's not something that we've looked at really, though. The very first architecture, and really it didn't have a name at the time, but we now refer to it as the monolithic architecture. So there are about, let's say, 3 or 4 architectures that have evolved over time. And the evolution of the architectures that are being recommended are reflected in the entities that I mentioned on the previous slide. The entities that I mentioned, these guys here, they always apply. It's always good to try and meet up to these characteristics. And architectures that have evolved over the years have all been aimed at trying to maximize testability, deployability, etc., etc. But the very first architecture, which didn't really have a name at the time, but we now refer to it as the monolithic architecture, how was that characterized? And we're particularly concerned with maybe server side of an application now, as opposed to the UI side. Well, a monolithic architecture is categorized by the fact that there's just a single code base. So all of the code for the application is contained within, if you like, within one GitHub repo. It's deployed as a single unit. So the entire application is deployed as one entity or package or archive, which is not the case, by the way, in the applications that we've been developing in this module. The individual lambdas, when we do a CDK deploy, if we make a change to a lambda, for example, just one lambda, and we have, let's say, 10 lambdas, we make a change to one lambda and do a CDK deploy. The CDK is clever enough to realize, well, I only really need to redeploy one lambda. It doesn't go redeploying all of the other ones. However, in a monolithic architecture, and we are certainly not following a monolithic architecture in this module, hence the name of the module, distributed systems, or distributed systems, distributed applications. But with the monolithic architecture anyway, it was deployed, the entire application was deployed as one unit or package. Typically, though, these monolithic architecture applications, they do live for a long time, so a lot of tools have evolved that support the development and maintenance of applications that implement a monolithic architecture. So they have that going for them. And that's the availability of these tools is really because this architecture has been around for a long time. In terms of scalability, the scalability happens horizontally. Essentially, you've got to make multiple, you've got to have multiple instances of the application up and running. I think if you think of in the context of AWS, if you think of EC2 and you deploy an application onto EC2, what you're really deploying there is a monolithic architecture application. And we know if we want to scale up, then we just create multiple copies of the EC2 instance. That's how scalability is met when you're running a monolithic architecture application inside an EC2. And that is really what horizontal scalability is. To update the code, okay, if we want to make changes to the code, we make changes to the code, but we have to redeploy the entire application. We can't redeploy a part of it. Unlike with Lambdas, which we can redeploy a particular part of it. So there are the characteristics of the monolithic architecture. And in fairness, the monolithic architecture satisfies all of the ilities from the previous slide, as long as the application is a fairly small application. It's when the application size starts to grow that the monolithic architecture starts to deteriorate in terms of meeting these ilities, which is why very few applications are actually following this monolithic architecture now, unless it's a small, single user or small number of users trying to access it at any particular point in time. If you're talking about a large user base, then monolithic architecture is probably not the way to go. This is a typical kind of visual representation of what I mean by monolithic architecture. And when I saw this image, which I just grabbed off some article somewhere along the line, this is actually very typical of the type of fourth-year projects that we would have been getting, oh gosh, maybe 15 years ago now at this stage, or probably even a little bit longer, but an awful lot of them would have been using this kind of architecture and technology stack. And so what we're trying to get across here is, here's my application. It's broken up all right into modules, which, okay, I'm using, it's a modern term, using the word service here, but it's broken up into modules. But each of these modules is, let's say, a group of classes that implement some overall piece of functionality. So all the accounting functionality is implemented by the various classes that are inside here, and some of the methods of the classes are public, so they can be invoked by other modules, and the rest are protected or private. The code is deployed as a single unit. WAR there stands for Web Archive. The notion here now is this is your typical kind of e-commerce web application. So you have all of your code. Admittedly, it could be all inside in one GitHub repo. But in terms of deploying it, what you've got to do is create a WAR file, which is a Web Archive file. There's tools to do that for you. So it essentially gobbles up all the code and packages into one unit. And then you deploy that WAR file onto an appropriate server platform. the dominant server platform was a platform called Tomcat. So Tomcat is an application, a web application server. And so if we bring this forward to more modern day thinking, you could deploy the Tomcat server in an EC2 instance, and then, if you like, maybe mount your WAR file into the Tomcat server running on your EC2 instance. That's how you might do it today if you want to stick with this monolithic architecture and you wanted to run it on AWS. The I don't know, these kind of brown boxes kind of represent the scalability side. So, you know, if you want to scale up, then you've got to have multiple instances of this brown box. I'm saying it's brown, I'm not sure what color it is. And the brown box really kind of is a bit like an EC2 instance, right? Although we would have had individual servers back in the day, but you have to replicate your servers. That's how you achieve scalability. And in front of all of that is some sort of load balancer, which takes care of directing requests to load balancing the various requests that are coming into a particular instance of your application. So that's how it might look. And typically you only had one database at the back end, and all of the instances were talking to the same database. So the database was certainly a bottleneck, and you had to take care of the fact that you had multiple instances now potentially trying to access the same data, however you dealt with that. Drawbacks. Well, as the application grew, which hopefully it would because it was a successful application, then that meant that, you know, your software development team grew in size as well. And the larger the software development team, the more difficult it is to manage it. And one of the things I hinted at earlier on was saying that we'd like to be able to break up our software development team into small autonomous groups. The autonomy is important. You can certainly break up a large software development team developing a monolithic application. You can certainly break it up into small teams, but they can't really work autonomously, because if one team, if we go back to here, if one team, you know, if you've got a team responsible for each of these services, okay, 3 people working on this, 2 people on this, whatever, then if one person wants to make a change to their particular service within a small team wants to make a change to their service, yes, they can change the code, but certainly in terms of redeployment, they have to make the other teams aware of the fact that we want to do a redeployment of the application, just in case, you know, the other teams are in the middle of developing some particular feature and it's not ready for deployment yet. And so that, you know, that can be a concern. So the development team grows and it just becomes more difficult to manage the whole and coordinate the entire process, development and deployment process. As the application grows, the modularity tends to break down as well, because what tends to happen is we start making, certainly in terms of resolving bugs, we start making changes that are breaking the modularity boundaries, because the pressure is on to fix the bug. So, you know, a lot of hacks tend to be implemented and the modularity breaks down. It starts off as a really nice modular application, but as it grows over time, and maybe not necessarily because of bugs that are being resolved, but as new features are being requested by your customer. One of the first slides I mentioned, it was this idea that the business environment is rapidly changing. We need to be able to adapt to it. So your customer is maybe making demands for new features, but this new feature doesn't neatly fit into one of the modules that make up our application from our initial monolithic architecture. And so a feature now is spreading across more than one module. And so the modularity boundaries tend to get more blurred, and hence the understandability of your code tends to get become confusing as well. Decreased maintainability, which is the point I was just making there. Decreased testability. When we have a nice modular breakdown, and the modules are self-contained in as much as they can be within a single code base, then testing is actually quite easy to do. If I go back to here, it's quite easy to write tests, a set of automated tests that just focus in on a particular module. And even if that module is communicating with other modules, then you can essentially use a technique called mocking for the other modules. You don't have to have the actual other modules available to you when you're testing this one. You can use have a mock of them, and that facilitates the communication that would normally be going on between modules. So the ability to test a module in isolation is quite easy to do when the module boundaries are clear, but it's obviously less easy to achieve when the module boundaries are blurred. Technology becomes increasingly obsolete. Well, it's for sure. If your underlying third-party packages, and maybe even lower than that in the stack, they become more out of date really over time, and it becomes difficult then to modernize it. This is a nice graphic I found somewhere, and it kind of tells the same story really. As the size or complexity of your application grows, and this is Maria representing the growth of my applications, then the entities tend to go in the other direction, and you can't just get around that really, no matter how well you've structured your code base from a modularity point of view. It just breaks down eventually. For that reason, a new architecture, new at the time I'm saying, I just looked up this yesterday, it was around 2011, 2012, when we started to read about something called the microservices architecture, which really was an alternative to the monolith because of the various deficiencies in the monolith architecture. And one of the first people to talk about this architecture is an individual called Martin Fowler, whose name you might have come across. He would be globally recognized really in the software architecture world. So the microservices architecture, I'm saying, is an architecture that structures an application as a set of services. Service here now, even though I use service in my monolith picture earlier on, service here is something that runs. Sorry, can I just go back? Sorry, just back 1 second. The assumption here is that all of this code is running inside a single operating system process. I guess that's taken as read, really, if I think about it. But it is running within a single operating system process. Whereas in the microservices architecture, your services are running on within separate processes, and in fact, more likely, they're running on separate machines, or certainly they're running inside a separate VM. And so any inter-service communication has to be across a network, essentially. So we break our application up into services, where a service is characterized by it's organized around a particular business capability. That's kind of from a modularity point of view. So a service should be focused on one part of the business that you're developing the application for. Now, sometimes it can actually be quite difficult to come up with the right set of services, but we'll just kind of gloss over that. I'm mentioning some kind of classic examples here. Secondly, a service is independently deployed, which isn't the case, was not the case with the monolith. With the monolith, it was deployed as one unit, whereas now we can deploy each service separate from all other services. And consequently, each service is scalable on its own. If we wanted to scale up on the monolith, we had to scale up the entire application. But typically what happens in applications is it's one part of the application that is being hit by heavy traffic. Other parts less so. But with the monolithic architecture, we have to scale up the entire application just because of heavy traffic hitting one part of it. Whereas in the microservices architecture, we scale up the particular part or the particular service that's being subjected to heavy workloads. And you can visualize that really now if we're talking about running this on AWS. We certainly can scale up. Did I mention that? We can scale up Lambdas. Well, whether I did or didn't, individual Lambdas can scale in isolation from all other Lambdas within an application. A service here now, a service is bigger than a Lambda, really. It could be a Lambda, but it would be a very large Lambda. A service is certainly smaller than an EC2 instance. It's probably larger than one Lambda. Typically, what it might be is maybe a Docker image. Don't know if you've covered Docker anywhere along the line, but it's larger than a Lambda typically. It might be a small subset of Lambdas, all right, that collectively implement some business capability. Moving on, it's highly maintainable. Well, highly maintainable because the sheer volume of code in a service is obviously smaller than the volume of code in a monolithic architecture, because a service is just one part of the application. So that's why maintainability is improved. You know, there's just less volume of code that you have to get your head around to understand the workings of the service. And because it's a smaller and more maintainable, it's also more amenable to automated testing. So looks like the microservices architecture is it's better than the monolith because the drawbacks of the monolith are really being addressed by the microservices architecture, which is exactly where the microservices architecture came from, really. Fowler looked at the drawbacks of the monolith and came up with this alternative architecture to overcome those deficiencies. So this is my visualization of it. So each service now is a separately deployable, scalable entity. And you could think of this, let's say, you could think of it as a very large Lambda. There is some inter-service communication still needed. The other characteristic that was unique to the microservices architecture is the fact that each service had its own private database. Now, the downside of that was, though, that it meant that certain information might have to be replicated across databases. If you take a simple example, let's say, of a customer's address. So this database presumably would have information about customer addresses in them, but maybe the marketing database might have customer address as well somewhere within it. And so when a request to change a customer's address comes through from the browser, it has to be handled by two services and it has to be updated in my two databases. But what happens if the accounting service is down and the address is not updated, but the marketing service is up and running and it is updated? Now there's a problem. And so the microservices architecture introduced some problems as well. But anyway, from a characteristic point of view, this was one of the aspects of it that people found difficult to kind of comprehend initially, was this idea that each service had its own unique and private database. There was no sharing of a database, as opposed to the monolithic approach where we had one database and, you know, every request was going to hit that single database. Anyway, I don't want to get dragged into the whole database side of the argument. It's more this idea of the services being individually deployable, scalable. The code base is smaller for each service than it is for the entire monolith. You can test each service in isolation, there or thereabouts anyway. Benefits, maintainability, I've mentioned. Modularity, yeah, because each service now is packaged as an independent and has a clear API. That's okay. Evolvability, that's another nice aspect of it. This service here, we might write this in Python because it's best suited to it. Whereas this service might be written in TypeScript. This service might be written in Java. So there's no problem with that. They're completely independent. And so, if you want to update this service, because they're written using a different technology stack, you can quite easily upgrade this service's underlying technology, like update the various packages, and it doesn't impact on anything else. And it can be done without having to concern yourself with the other services. Testability is better as well, because you can certainly now test each service in isolation, and again, kind of mock the interfaces that it has with other services. Again, I don't want to get dragged down into the testability, because I'm pretty sure you haven't done a whole lot on automated testing, so you can't talk about something you're not familiar with. Deployability, I've kind of already spoken about. We have better scalability as well, and better fault tolerance. Each service now can scale up without having to scale up the other services. And the fault tolerance, yeah, well, I mean, if for whatever reason this service here is out of action, then that doesn't impact on requests coming in for the other services. Whereas in the monolithic approach, if one particular module threw an exception and crashed the application, the entire application is down. So by choosing a microservices architecture, you got all of these ilities improved, notionally anyway, and these actually contributed to the other part of this triangle of success, if you like. I'm just going to move on from there, really, because I don't want to get too bogged down in it. But of course, there were challenges with the microservices architecture now, because our entire application is spread over a number of, potentially separate VMs running across a network. Then we've got a lot of inter-process communication going on, which wasn't the case in the monolithic approach. And anytime you've got communication across a network, then you've got the problem of partial failure. If one service is partially down or temporarily down, then that can impact on the other services. And again, going back to here, if there's a request coming in for this service and it has to communicate with the accounting service, but it is temporarily down, then what does this service do? You essentially have to build into your software, you have to build in for that possibility, which wouldn't have been a concern in the monolithic architecture. You've got to essentially program the possibility of partial failures in communication that goes on between the services. Something, again, that we've kind of ignored in the case of Lambdas, but we're kind of taking the happy path from what we've been doing so far. Testing, end-to-end testing, okay, you can, with the microservices architecture, you can automate the testing of each service in isolation, which we often refer to that as unit testing. But if you want to run some tests across the entire application, this kind of end-to-end approach, then there are problems with the microservices architecture, because it's now running across a a network of nodes essentially. And how do you build that into your automated tests? Although there are tools that can deal with it to a degree, but it's certainly a new concern that wasn't there in the monolithic architecture. And okay, we can talk about being able to deploy each service in isolation and scale it in isolation, but because there are some inter-service communication requirements, then you can't just blindly redeploy and update to a service without concerning yourself with the other services. Can I just come back? There's one point I do want to make. I kind of skipped over this slide, but there is one important point that I want to make in relation to this slide, and one of the benefits of the microservices architecture, which is in relation to the organization of your group of people that are involved, that are responsible for an application. You see, with what the microservices architecture allowed the software house to do is to break up the overall software group into small teams, where each team was now responsible for a particular service. And they could, to a degree, work autonomously. They could evolve a service without needing to consult with the other teams that are responsible for the other services. As long as the interface for their service was not changing. So, they could change the internals workings of the service. They could change its software stack. And that's not going to impact on any of the other services. So they had, to a certain degree anyway, a degree of autonomy in what they wanted to do. And that autonomy meant that, they could move their service on and upgrade their service without being too concerned about the other services and the other teams. Again, that wasn't the case with the monolithic architecture. So you get these small teams now being responsible for a product or a service. When the microservices architecture was being touted as the alternative to the monolith, then one of the problems was, well, how do we migrate our monolithic architecture application over to a microservices one, assuming that you've got this application that the customer is very happy with, but it is, from an architecture point of view, it's following an old architecture. How can we modernize it into a new architecture? That certainly wasn't, which we call migration. That migration was certainly not straightforward. Now, there are strategies that emerged over the years to how you should approach the migration. One of them was called the Strangler pattern. You can read it up if you want to yourselves, but it certainly was not a straightforward, as you might imagine, not a straightforward task to migrate a monolith over to a microservices architecture. And also there was the kind of practical, from a design point of view, there was the issue of how do you identify what constitutes a good set of services and good service boundaries. Okay, in the example that I have on the slides, it's kind of nice and neat, the accounting service, the marketing service, they all kind of mirror the structure of your typical business organizations, but some organizations may not be that neatly structured and may not map over to services in a microservices architecture in that kind of neat way. So from a design point of view, that was problematic. The main downside of the microservices architecture was what is kind of characterized as the microservices monolithic anti-pattern. And it is that at the end of the day, the services did need to communicate with each other. And so there was a lot of inter-service communication necessary. Now that might be a reflection of poor decision on service boundaries, But even with good service boundaries, you still had to have, it turned out, a lot of inter-service communication going on. And so in a way, we were back to the whole problem with the monolithic architecture, in that, okay, I was saying up to now, you could change each service. Each team is responsible for a service, and they could make changes to that service independently of all of the other services. That sounded nice in theory, but if your service is being used by lots of other services and there's lots of communications, then you probably do need to consult with the other teams that are developing the other services about the changes that you're making, especially if the changes that you're making impacts on the service's API or interface. So it wasn't that kind of silver bullet that a lot of people thought it was initially, the microservices architecture, mainly because of this inter-service communication reality that existed. And the problem of that inter-service issue is really back to, or is what's often referred to as the coupling problem. Coupling or dependency relationship. In the diagram here, I'm just showing you, let's say, two services. The specifics of them aren't really important, but so these two services depend on each other, or more particularly, this service here depends on this one. What I mean by that is, okay, the specifics are, it's an order service and a customer service. So a request comes in to a new request comes in, and the order service needs to send a request to the customer service to what's the specific? Let me just check. Sorry, to reserve credit for the particular customer. Okay, that's just the specifics of it. So it sends the request to the customer service to reserve credit. It does its processing and comes back with a response. And then the order service can now respond back to whatever client is over here. So what we say is that there is tight coupling between these two services. And a consequence of that is, if this service is down, then when a request comes in, this service cannot complete the request because it has a tight coupling or dependency relationship with it. Now, I'm saying down here that coupling is inevitable, really, to a degree, but it's how you satisfy that coupling requirement is kind of what's at issue here. So coupling is inevitable, but what we try and aim for is what is referred to as loose coupling. What we have above in the diagram would be categorized as tight coupling. So that's the nub of the problem with the microservices architecture and this microservices monolithic anti-pattern from the previous slide. The fact that there could be too much tight coupling between the services that make up your overall architecture. And can we somehow reduce, at least, if not, certainly probably not eliminate, but reduce the amount of tight coupling between services somehow? At the bottom here, I'm saying that there are two types of coupling: runtime coupling and design time coupling. Runtime coupling is what I've actually been just describing, where there's actual runtime communication going on between two services, and my service on the left can't process a request until the service on the right has responded to its request. That's runtime coupling. Design time coupling relates to, where if you have to make changes to the code for one service, if you need to communicate the changes that you want to make to other service teams, then that would be characterized as a design time coupling. Because if you want to make some code changes to your service and you know that other teams who are developing other services are communicating with your service, then you may need to or you may have to collaborate with them. And we'd like to have our teams, our individual service teams, work autonomously. That's one of our objectives. So if there are design time couplings, then that kind of goes against that autonomy objective. Design time coupling requires service teams to collaborate. Okay, I've made that point. And okay, I'm saying here's a statement that, as a statement, I'm saying we try to minimize design time coupling. Okay, that might be objective, but how might you achieve that? And I think I talk about it on the next slide, or this is a kind of a visualization of what you should be trying to achieve. So for a particular service, you try and make sure that its API or its interface is as small as possible and as stable as possible. And if you can achieve that, and okay, I'm not giving you any guidance on it because we don't need to know it essentially, but I'm just making you aware of these things. If the API of a service is small in terms of just volume and it's stable, it doesn't change over time, then it doesn't matter how much changes you make to the internal implementation of the service, as long as it doesn't impact on the API, then that's going to benefit your overall design, and the team that is responsible for the service can now happily evolve that service by making changes to the code or to the technology stack. As long as the API isn't changing, then they can work autonomously, which is what we're trying to get at. So design your services like icebergs is this kind of catchphrase that's often used. Kind of makes sense, but again, you would need some guidance as to, well, how would you approach that, or what are the good practices and bad practices towards achieving that? When we don't really have time to get into that, unfortunately. Another aspect of this coupling is what you should try and avoid is having two services or more than two services using the same database, because the database then becomes the bottleneck, if you like, and it almost becomes a facilitator of communication between your two services. Now, okay, when I showed you the microservices architecture initially, I said each service has its own personal database, if you like. That was the ideal scenario, but in reality, that didn't materialize. And so, but again, because it didn't materialize, that introduced this coupling problem. So coupling doesn't necessarily mean direct service-to-service communication, whether that be at runtime or design time. It can also mean via a shared database. So in terms of objectives, anyway, that's how you, from a design time coupling perspective, that's how you reduce tight coupling, by designing your services like icebergs and don't have shared databases. The other, sticking with the same coupling issue, we're talking here about the synchronous IPC problem, which is another way of approaching this coupling problem, or viewing this coupling problem. So I'm saying a distribution. So our services are now running on separate nodes, if you like, and they're communicating over a network. Hence, they are distributed. But that distribution, we're saying, is not free. And what we mean by that is because they're communicating across a network, then there's the possibility that the network connection is down, or that one of the services is temporarily down. So, which kind of leads to the whole area of fault tolerance. And you have to build into your software that reality, and you have to allow for that possibility to arise in a particular inter-service communication scenario. You kind of have to build fault tolerance into your code. I mentioned this a few moments ago. We haven't looked at it, but it's something that we just need to be aware of anyway. So it's saying here, don't treat your services as if they're just programming language level modules, because they're not. Whereas in our monolithic architecture, our services were at the programming language level, but they were all running inside a single operating system process. Whereas now that's all changed. They're now communicating over HTTP, and so that simple, well, it's probably not a simple technological change. That surely must mean that the way we code our services has to change as well, because they're no longer running within a single process. IPC is relatively expensive. Well, for sure, it adds latency to it. Sorry, now just let me synchronous. All right, so we're expressing the problem with inter-service communication and this tight coupling. We're expressing it here in terms of availability, because what the graphic is telling us is that if we clearly we want to maximize the availability of a service, but really when you've got tight coupling between two services in a microservices architecture, then the availability of one service is influenced by the availability of the other services that it communicates with. So if we just take the simple scenario here of two services, then the availability metric for this service here is equal to the availability of that service itself multiplied by the availability of the service that it depends on. And clearly that's going to reduce the availability metric for this guy if it's somehow being influenced by another service. We'd like the availability of this service to be purely measured in terms of how frequently the service is up and running. Which brings us on to asynchronous communication. Previously, or up to now, the communication between our services in the microservices architecture has been synchronous. Yeah, there's synchronous communication going on here and all the problems associated with that. If we could make this communication asynchronous, then certainly from the availability metric point of view, the availability is going to increase for my service on the left. How do we achieve asynchronous communication between two services? We use some sort of a messaging broker or messaging infrastructure. Sorry, no, I'm just checking my watch. Yep. So we're nearly there. I know this is heavy going now, but so the way you solve the coupling stroke dependency relationship problem associated with microservices architecture is to introduce asynchronous communication between services. If that makes sense, it may not always make sense, but where it's possible, that's what we should do. And this is really what we're going to look at for the remainder of this module, actually. We're going to look at how we implement from an AWS infrastructure point of view, how we can implement these kind of message brokering infrastructure, which are also called services in the language of AWS. And so now it means that when this order service needs to communicate with the customer service, it's using some sort of messaging channels. And so the order service, okay, a post request for the order comes in, the order service, it sends a message to the message broker, or it places a message, if you like, onto this queue here. And the customer service is listening to this queue for new messages. And anytime a message arrives, maybe not on a one-to-one basis, there could be a group of them, it deals with the message in its own time. If it happens to be unavailable, the message is just going to remain in the queue until it becomes the customer service becomes available again, or it's back up and running again. Anyway, it processes the messages on that queue and puts its responses onto a separate message queue. And this message queue is being monitored by my order service. And it eventually responds back to the requester, whoever the client is, on the synchronous request that's coming in over here. Now, clearly there are implications to introducing this middleware, if you like, as it might be referred to. You're no longer getting the response coming back from this service. It might give an initial response, which is essentially saying, I received your order. And it's only later when the customer service places a response into this queue and the order service processes it. It's only then that it can tell the client on the left, your order has been successfully accepted, let's say. So there are consequences to having asynchronous communication between services as opposed to synchronous. But the benefits are that now really our two services now are decoupled, or they are independent of each other. We can assume that whatever piece of infrastructure is providing the messaging or taking care of the messages, we can assume that that is reliable. I mean, that's been taken care of by, in our case, the AWS platform, and we can be happy that that is, in terms of availability and reliability and durability, etc. That's never in doubt. But in terms of our services, they are now decoupled, and now this service, from, in terms of all of the entities that we talked about earlier on, it is certainly independent of every other service. It can be tested independently, it can be deployed independently, etc., etc. And the team that are managing, the service can now work in isolation and not worry about the customer service team, because really all the order services communicate with is this piece of infrastructure, which is generic. And I found this, this is the last slide, you'll be delighted to hear. I found this slide on somewhere, and it really, it's a nice visual representation of what we're aiming for today in terms of architecture. Now, okay, there's a bit too much going on in this slide, but we're really only interested in, you know, what's going on here, because it's the back end is all we're concerned with. We're not dealing with client side. And so what we're trying to get across in this image is that, okay, there may still be some inter-service communication needs. There may be need for synchronous communication between some services. But in the majority of cases, there is some sort of messaging infrastructure or broker that is now being used to facilitate inter-service communication. And so our services are now truly independent of each other. And so what we want to look at is how can we achieve this using the AWS platform. and I don't have this. Oh yeah, this is the slide actually. So there are two services that we're going to look at, SQS and SNS. And these two services are satisfying, to a degree anyway, what's being represented by my red box here. Okay, so I'm going to leave it at that. So we went, oh yeah, well, I guess the final thing is this architecture that we're looking at now is the modern term for it anyway, is event-driven architecture. I think previously it was called message-driven architecture, because a message, in a sense, a message is conveying some event that has happened. If you go back to our, our example here, the event, if you like, is an order has been placed. That's the event that would go onto that queue. The event that goes on to, that is wrapped up as a message on this queue, is credit has been granted to a customer. Okay, so messages, if you like, are wrappers for events, where the event is some sort of business related event. Hence, that's why the term event-driven architecture is the kind of modern label that we put on this architecture that I'm showing you. Okay, so I did say it's all theory and all talk, and it's never easy really to sit through all of this kind of stuff. But hopefully when we start to practice the implementation of this side here, and then maybe you can go back and reflect on this notion of event-driven architecture, the idea that it's trying to reduce, if not eliminate, coupling between the individual components that make up your architecture, where a component is what we call a service. That's the idea, and so that now satisfied a lot of or resolved a lot of the drawbacks with the classic microservices architecture. Okay, I'm going to leave it at that, and I guess I'll talk to you in next week's lab. Thanks for hanging in there. Bye-bye.